Hi, Professor Berryhill. This is my presentation for Astronomy 11. This has to do with our magnetic black hole. I wanted to give a summary about it and more stuff that are some cool facts that I can tell you about. Astronomers on a quest to see a black hole. It's not as an exotic name as it sounds. Despite the reputation, black holes are lousy comet vacuums. They suck up only a fraction of the gas in the disk that grid them, flinging around or ignoring the rest. It's these glowing disks of the gas that undermine the beast in itself. The black hole's extreme gravity bends light from the disk around its boundary and creates a telltale silhouette. The shadow, quote unquote, of the event's horizon is there no point. So basically, this is a sun. It looks like a sun, and then it's all remainder of the sphere is all red, with a portion of it being black. And that portion of it that's black is a black hole because you can see it within the color of the sphere, and the sphere itself is orange. Its strong gravity that bends light around the Milky Way's holes, black in the stimulation, leaving a silhouette against the glowing background. So that was an explanation of an image. At least that's the idea we haven't seen in the shadow yet. But in the Event Horizon Telescope aims to do it. And the EHT is a world-spanning project linking together radio antennas from Hawaii to the South Pole to work together as a gigantic planet-sized virtual telescope called an inframeter. So basically, this telescope would be from Hawaii to the South Pole and be able to cover all the galaxies, be able to see what's in space, what we're not seeing, and it's basically a radar between that radius itself. As a part of the endeavor, Michael Johnson, it's a Harvard alumni. He's also an instructor there in astrophysics, which is astronomy and physics, and other members of the EHT collaboration have now set a mini version of Growing Network to watch the magnetic fields dance in the skirts of our galaxy central black hole, which we learned about in the constellation with Sagittarius, and this configuration is formed in the area of Sagittarius A. Magnetic field runs all over. The astronomers use telescopes in Hawaii, California, and Arizona. Their observations synced in the atomic clocks to peer into the black hole's inner sanctum. With only 3 sites, a few nights of worth observations, they couldn't reconstruct a complete image. Instead of seeing the whole elephant, they were seeing now is more like an ear and a bit of a trunk. But those bits aren't good enough to them. Start detangling what's going on. So, in an image I'm going to explain is a sphere, a moving sphere with a black hole in the middle with its energy. So the concept of this was showing the area of Sagittarius A, the black hole at the center of our galaxy, surrounded by a hot disk of the ionized gas. Blue lines trace magnetic fields. We know blue dwarfs have to do with the temperature. That is the biggest temperature you're going to get over a small dwarf. When it's blue, it's the hottest at its point. Astronomers using the Events Horizon telescopes have measured our black hole's magnetic fields for the first time, resolving structures as small as 6 times the size of Event Horizon. The fields are disorderly and changeable, like intertwined spaghetti. These fields team found are either on the disk or the jet. So, explaining this explaining this is basically a sphere and the surroundings of it, and the blue being the lighting so strong, and the black being the black hole itself, which is the suction of everything. Bringing theory to life. So basically, the results of the great news of the theorist, says Chris Reynolds, which studied at University of Maryland, who has spent his life working on black holes. It's taken decades to understand why gas in the accretion disk falls into a black hole at all. It should just orbit forever because the gas is too tenuous for the friction to slow it down. Astrophysics finally realized a couple of decades ago that the magnetic field swirling around in the disk would tug on the gas, pumping up the turbulence and robbing the gas from its angular moment, allowing it to fall into a black hole. So all in that process is what is being allowed and sucked into the black hole, which is itself the gases that we know of. A black hole is not it's not destroying anything. It's only intaking those gases that are put out there. So there's certain things black holes don't take, which is now proven in 2015. Here's a quote from Reynolds, but it all is very much in a theoretical domain, quote unquote. We believe this is how disks must work. Because we don't have any better ideas, the new EHT observation shows that theorists might have been right on track. It's honest to goodness measurements of a real black hole that are getting the crux of the issue. For now, the team can't tell if its magnetic fields are part of the jet of a disk, but it looks like they're only seeing one or the other, not both, Johnson says. Astronomers don't know whether Sagittarius A has jet, but its stimulation jets often shoot from the slower feeders like our galaxy's black holes. So, in all, basically, they're still doing more discoveries on the black holes, and we don't have any final theories about how it's formed and what it's intaking. We just know for now that it is intaking certain amount of gases and not intaking everything. So the black holes, like Reynolds was saying, are still being determined, and it's an all theoretical domain. So that was my presentation for part two of Astronomy 11, and it's related to black holes, and I hope you enjoyed. Thank you.